All right, this is going to be the first video for our two-sample inference unit. So this is going to be the introduction to Chapter 10. We're going to now extend our statistical knowledge of inference to two samples from one sample. All right, and we're going to now see how we're going to do that. First, we need to discuss the difference between independent samples and paired samples. So this is going to be a big difference. So remember in Chapter 8 and 9, we discussed constructing confidence intervals and performing hypothesis tests on data from a single sample. So we usually had just one sample that we were discussing. Sometimes when a match pairs t-test, we would pair data together, but still it all came from the same sample. In this chapter, we're now going to expand this inference or these inferential procedures to include independent random samples. So here we're actually going to start taking two samples and using the same type of tests in order to perform inference. So instead of it being a one sample test, we're going to talk about how to do a two sample test when we actually have two samples there. So the difficult part here would be trying to figure out when the samples are independent and when they are dependent. So remember that for match pairs t-test, the data are dependent, and that means that the assignment of treatments would depend on how you kind of randomly assign treatments to subjects. And in independent random samples, you actually have two samples, but you're going to measure the same variable, but within those two separate samples. Let's take a couple look at examples talking about independent random samples here. All right, so let's first define it, I guess. Independent random samples are samples that come from two different sources. So one sample does not influence or affect the second sample. So independent random samples come from two different sources. It could be from like maybe two different time periods, two different classes. It could be anything similar to that. So you're just going to make sure that one sample has no effect or influence on that second sample. That's different from a paired random sample. So these are oftentimes from one sample where multiple data were collected. So that's going back to Chapter 9 when we discussed matched pairs, when we're talking like before and after effects, when we're talking about left hand versus right hand, pre-test versus post-test. All right, that's usually from one sample. So the main difference here between those two is going to be from two samples to one sample, all right, and vice versa. So again, independent random samples are samples that come from two different sources. So one sample does not influence or affect the second sample, whereas paired samples are oftentimes one sample where multiple data were collected, and that's the oftentimes one that we know as a matched pairs design. Let's talk about an example. So for example 1, to test the effect of background music on productivity, 30 workers are observed. Each worker is assigned a score of 1 to 10, 1 being not productive where 10 is being very productive. For 1 month, they had no music, and for another month, they had background music. At the end of the second month, the difference in the scores are compared. So when we're talking about, is this an independent random samples, like from two different places, or is it a paired random sample? All right, for this one, this is going to be paired because you have one sample of 30 workers where they receive one treatment 1 month, but a second treatment another month, and then you compare the two. So basically each worker is going to get both treatments and their differences were recorded. So they had the productivity with music from 1 to 10 and the productivity without music 1 to 10, and then wanted to test a difference. So maybe they might find statistical evidence that productivity is increased with music and not without music. So maybe they might start playing music or something. But I guess the type of music would then matter. I don't know. But for number 2, a random sample of 10 workers in plant A are to be compared to random sample of workers in plant B about their feelings on the working conditions within their plant. So here, this is going to be a good example of what's a independent random sample. And the reason that this is going to be independent random sample is that you have two separate samples. You have 10 workers from plant A and you have 10 workers for plant B. And then you're going to ask them the same question. So since they work at different plants, those opinions are going to be independent of which plant they work at. So maybe plant A really cares about their employees, making sure that they're well taken care of, they get the time off that they need. Maybe they're given like lunch once a week, whereas plant B, they don't really care about you. So maybe those people might not feel as good. So since they work at different plants, the different operating procedures may cause them to either like or dislike their working conditions. All right. So since they're from two different samples, that's going to be the main issue there. Number 3, to compare the average weight gain of pigs fed in 2 different rations, 9 pairs of pigs were used. The pigs in each pair were pinmates. One pig was fed the current ration, whereas the other was fed the new ration. All right, so what do you think that this is going to be? Is this going to be an example of an independent independent random sample or a paired random sample? All right, and if you guessed it was paired, you were right. So this is, again, one sample of 18 pigs that were paired, making 9 pairs. And these pigs were fed 2 different rations, but they were matched together and because of their similarities. So you're assuming that the pigs are the same breed, same height, same weight, same color. Keep them as similar as possible, but then you're going to feed them to 2 different rations and then figure out which one is going to increase that weight gain, because you want them to be I guess as fat as possible. Who knows? All right. We're going to now discuss what the sampling distributions with independent random samples looks like. So when we independently random sample 2 groups of individuals, we often want to discuss the true difference in the mean/proportion between the groups. So here we're going to be interested in finding the difference between 2 means and the difference between 2 proportions amongst these groups. All right. So we're going to be subtracting since we're trying to find the difference. To do this, we will describe the sampling distributions of the difference between the groups. We need to first talk about that. So we're going to extend our inference procedures to 2 samples, and oftentimes we're interested in the difference. So we need to first talk about that sampling distribution. Here's a graph of both the sampling distribution between the difference of 2 proportions, which is on the left, and the sampling distribution the difference of 2 means on the right. So again, the p there, p hat sub 1 minus p hat sub 2 gives this away as being a proportion, whereas the other one is going to be a mean. So you should be able to recognize and figure out which one is going to represent a proportion versus representing a mean there. Okay. Let's first talk about the sampling distribution with independent random samples for proportions. So given that you have 2 independent random samples, big idea here is that they are independent random samples, and you have size 1, and this is going to be from the first sample, and size 2, because this is going to be from the second sample. So it doesn't mean that the sample sizes are going to be equal. They can be different, which is fine, but you need to make sure you notate them as separate. All right. So here, given that we have 2 independent random samples of size N1 and N2 that are chosen from independent populations, first, the shape of the differences of the proportions of 2 populations is going to be approximately normal if we check some conditions, and this is going to be sounding very familiar. We're going to talk about N1 P1 being greater than or equal to 10 and N1 Q1 being greater than or equal to 10. Now, this is usually the condition that we talk about normality with 1 sample, but this is only going to cover half of our samples. So this is going to be from the first sample. But since we have 2 samples, we need to do it a second time, this time with N2 P2 and N2 Q2 being greater than or equal to 10. All right, you're going to continue to make that same statement where the sampling distribution of P hat is going to be approximately normal if you have those 10 successes and 10 failures. But this is how we're going to need to notate our sampling distribution. It's no longer of just simply P hat. It's of P hat 1 minus P hat 2, because we're going to be talking about the differences between them. All right. So making sure that you have that within your statement there. So it needs to be something like, therefore, the sampling distribution of p hat is approximately, of p hat 1 minus p hat 2 is approximately normal. All right, and you guys know that statement very well. You can just keep on going there with that. All right. For the second one there, the mean of the difference is going to be when we're going to take the mean of p hat, used to be just p, but now we have the mean of p hat 1 minus p hat 2 is simply going to be the difference between them. So it's going to be p1 minus p2. So the mean of the difference there is just going to be p1 minus p2. All right. Now the standard deviation gets a little tricky. The spread of the difference here is going to be the sigma of p hat 1 minus p hat 2 being the square root of p1 q1 over n1 plus pq or p2 q2 over n2. And some of you guys are wondering how we got that. So let's actually take a minute to go through that. So for this, how did I get that, I guess, difference here? If you take the sigma of p hat, that used to be pq over n, but this time we're going to need a sub 1. So I'm just going to add that sub 1. So it used to be just simply pq over n under the square root, but now we have to notate it with 1. So again, if I were to take a second sample like sigma p hat 2, that's going to now be p2 q2 over n2. We can't simply just subtract the standard deviations because we learned earlier within our units there that we can't simply just subtract standard deviations, nor can we add them. Remember that we can only take the variance here. So in order to figure out sigma of p hat 1 minus p hat 2, we need to actually take the variance of going to be of like sigma p hat 1. We're going to square that. We're going to add that to sigma p hat 2 squared, and we're going to take the square root of that. So this is when, remember, this is how we SAS. So in order to come up with this, we SASed to do this, okay, which means square add square root. So if you take this right here and substitute it in, that's going to be the square root of p1 q1 over n1, and that's all going to be squared, plus the square root of p2 q2 over n2, all under there squared. And you guys should know here that these squares and square roots are going to cancel out, leaving you with just the square root of p1 q1 over n1 plus p2 q2 over n2, which is going to be your standard deviation for the difference there. All right, so that's just kind of walking through how you kind of derive it. All right, so that's how we are going to derive that standard deviation of the difference between those two independent proportions there. All right, let's do it with means. It's very, very similar. Just kind of remember that we are going to go over some examples of this and use this. But this is just kind of getting, the notes basics out of the way here. But if you have, again, two independent random samples from size 1 and size 2. So the idea here is that they have to be independent random samples of size N1 and size N2. All right, again, we're going to talk about the shape of the difference of the means in the two populations is going to be approximately normal if the same conditions apply that we've already discussed in Chapter 9. So with means, remember, if the population distributions are normal, remember that's going to lead that the sampling distribution of x bar 1 minus x bar 2 is going to be normal. All right, remember that the central limit theorem here tells us that if both sample sizes are going to be greater than or equal to 30, then we can use the central limit theorem to talk about the sampling distributions being normal here. And if they are less than 30, then that means we're going to graph. Now, I don't want you guys to get so confused. This is not confusing. Remember, you're just going to do the same exact thing that we did in Chapter 9 with an additional sample, and we're going to be talking about the difference in means and the difference in proportions. All right, it's basically the same exact thing but double the number of samples. All right, so again, this is how we're going to talk about how to get the normality. So again, if the population distributions are normal, so are the sampling distributions, all right, of P, and this time it's going to be x bar 1 minus x bar 2 because we're talking about means. So for, if it's not normal, if the population distributions are not normal, then we're going to use n1 greater than or equal to 30 and n2 greater than or equal to 30 with a central limit theorem statement, then allowing that us to conclude that the sampling distribution of x bar 1 minus x bar 2 is going to be approximately normal. If not, we're going to have to graph, and this is when we're going to use our graphs such as a histogram or a box plot. So histogram or box plots here will work. I prefer box plots, but if you prefer histograms, that is also fine, but use one of the two because remember we're going to do this graphing within the calculator there. Similar to the last mean, for the mean of the difference in the proportions, the mean of the difference is going to be mu sub x bar 1 minus x bar 2. So the mean of that sampling distribution of the difference of two means is simply going to be mu sub 1 minus mu sub 2. So very similar. Instead of having P1 minus P2, we're now just going to have mu1 minus mu2. All right, and that's going to be how we're going to calculate the difference in the means. Now the standard deviation is going to be very, very similar. Here it says sigma squared 1 and sigma squared 2. Remember, we replace that. If sigma is unknown, we're going to replace that with s sub x, all right, to estimate. So either way, if you choose to use the sigma, if we know it, then we can plug that in. If we don't, we're going to use s sub x to estimate. So very similar to the very first time, I'm going to show you how this is derived. It's very, very easy. Remember that we had sigma x bar back in chapter 7 being equal to sigma divided by the square root of n. The only thing I'm going to do this time is add a little subscript 1 to all of those. All right, I add a little subscript 1 to denote that first sample. I'm going to do it again with sigma x bar sub 2 being sigma 2 over the square root of n2. All right. So here, remember, again, we cannot just simply subtract standard deviations. You can't just simply do that. We've got to remember that we need to take sigma x bar 1 and minus sigma x bar 2. And if we want to do that, we must square add square root. So we have to square sigma x bar 1. We must square sigma x bar 2. We must add them and then take the square root. So I'm now going to substitute this first one in here, this second one into there. So using substitution, I now get parentheses sigma 1 over the square root of n1 squared plus parentheses sigma 2 over the square root of n2 squared. And remember that if we're going to square these on the inside, I still have that big square root. That means I'm going to need to square sigma 1. So I'm going to get sigma 1 squared. I'm now going to square a square root. When I square a square root, it cancels, leaving us just with n1. Very similar. I'm going to now square sigma 2. So it's going to be sigma 2 squared. Over, again, I'm going to square a square root. So that means this square root and that square cancel, leaving us with n sub 2. And you guys should see that that matches our new formula. Again, this is all back from our chapter 6 using SAS, the square add square root method, to add variances together. All right. Feel free to rewatch this video in case you need to, but these are just the basic definitions in order for us to be able to do examples. On our next video, it's going to go through 2 examples of how we're going to use this to solve problems. All right. Until next time.